What's up, y'all? How y'all doing? Yeah, it's been a long day. I was walking around for 3 hours trying to do a scavenger. You probably just see me walking around wandering aimlessly and all that stuff. No, it's been fun. CactusCon is great. It's my first time here. First talk I'm ever giving here. And I think we're the last technical talk of the day, maybe. So we're going to get real technical. We're going to get real deep in talking about offensive debugging and looking at .NET memory dumps for gold, poops, as I call them, right? So who am I? My name is Leron Gray. I also go by Daddy Coco Man in some circles. You probably see me in your CTFs, hopefully winning. I hope I'm winning. My Twitter is or my social media is generally at MCOMI. I'm on the Azure Red Team at Microsoft. I currently have 2 degrees from Dakota State. I'm working on my PhD currently, so I'm a PhD student as well. I was in the Navy for about 10 years, got out, and now I became a red teamer, pen tester life, right? I do a lot of Python. Python tools are my niche. I'll write anything all day, every day. And I also CTF a lot, as I just mentioned, me walking around for 3 hours, and I'm not bitter about it. I'm also a nerdcore rapper. I go by the name Oh My. I was on the DEF CON tapes the last 2 years. You can also find my stuff online. I always got to promote my music, right? It's one of those SoundCloud rappers. So you always got to check out my music. What I'm not a software engineer, although technically it's in my title, security software engineer, but I'm not traditionally, I don't have a computer science degree, so I can't tell you things about like threads and memory. I can't get too deep into it. I know a little bit, but not enough. And I bring that up because we're going to be talking a little bit about that today in this talk. And I may not have all the answers, but hopefully if you have any questions as we get towards the end, I can answer them as much as possible. I'm not that great at WinDbg, which is also ironic because that's what we're talking about today. And so there's a lot of things in WinDbg I may not know about. You may find something that's easier as I show the demo. There might be things that are easier than the way I'm doing them. That's cool. I've only touched WinDbg in like the last couple months, and I learned a lot, and it's great. I'm not afraid to roast you because I'm from Brooklyn, and a lot of people think I'm just mean on Twitter. Nah, I'm just from New York. And I'm not any of these other dope nerdcore rappers. I'm definitely not Whitey Cracker or N80 of dualcore. I think that's pretty obvious. And the guy on the right, Dale Chase, who's also from Brooklyn, I'm not him, but he feels I look at him and I think he's about to steal somebody's girl, so maybe I wish I was him. All right, so off topic. Anybody know what this is? Before we get into the talk, can anybody see what that is? Yeah, balsamic. Yeah. So Elmo was on Jimmy Fallon the other day, and I didn't really get the joke on why people thought it was funny, because I'm from New York, and I've never heard the hard R said in vinegar. We don't do hard R's in my house. So I heard balsamic vinegar. I say balsamic vinegar. This is really off topic. It has nothing to do with the actual talk. It's just something that's really been bothering me the last couple of weeks. Anyway, so let's get into the actual talk. All right, so the agenda, we're going to talk some things about like offensive security basics, and then we're going to get into .NET debugging and some dump analysis with an attacker mindset. And finally, I'll demo a tool I wrote called Turd Shovel. This is not an official Microsoft tool. It's on my personal GitHub. They wouldn't let me. So it's about the basics. Having an attacker mindset. Generally, the questions you ask are, what's available to me? Like, what do I have? What do I want to make available? So what is my end goal of a pen test or a red team? And then how do I connect the dots from what I have to where I want to get? There's a lot of tools and frameworks that are out there that we use in our basic skills, right? Some command line tools, so you should know your way around a shell, Powershell, Bash, whatever. Some tools, some basic tools like Nmap that everyone uses, Metasploit. These are like the real basic things you might come across as you're learning offensive security. And then as you go along, you have to learn how to exploit and do proper post-exploitation, right? So the way that you loot an environment really depends on the type of environment that it is, right? It could be by the operating system, so the way that you look at Linux versus Windows, or the way that you would look at on-premises versus cloud is very different. Okay, there we go. And then some more intermediate skills, and these aren't really ranked in any particular way. I just call them like intermediate skills, right? As you start to grow in your offensive security mindset. A lot of these skills are supported by tools that people who are super smart have written and made it easier for offensive security people to use, right? So we talk about like enumeration tools. There's some popular ones that are used for CTFs, right? That just like enumerate everything. It's really noisy. Things like passing the hash, passing the ticket. These are more intermediate concepts about lateral movement and stuff like that. Doing things like non-default C2 profiles. So most people might use like Empire or what Bishop Fox is here, right? So it's like Sliver or something like that. And they may just use a default profile, but you have to eventually learn how to blend in with your environment, right? And so as you start to grow, you start to learn what you should and shouldn't do when it comes to using the tools that help supplement these sort of intermediate skills. Understanding source code is also very important. Even if you can't write code, right, it's very important that you are able to at least read and understand some concepts of what's going on, even if you're not completely familiar with the language. I hate looking at C#. There's so many people at Microsoft writing .NET, I don't like it, but I can still look through it, right, and sort of understand what's happening. And then finally, like, there's some basic exploitation, right? Everybody knows like buffer overflows in OSCP or the certified pen tester from INE, stuff like that. Then as we get more advanced, there's more software exploitation. We talk about binaries, right? Breaking protocols and breaking cryptography. There's some complex chains of attacks. Last year, there was a lot of Active Directory certificate service attacks, a lot of them, and printer attacks. All over the summer. Y'all was making a lot of work for people. I saw that behind the scenes. And then like anything to do with Kubernetes, it's just really advanced. So for offensive tools, debugging tools are typically not mentioned outside of exploit development. You might see things like GDB or WinDbg or OllyDbg, x64, all these debuggers and all these compilers, Ghidra, whatever. They're typically talked about in the concepts of either reverse engineering, malware analysis, but from an offensive standpoint, you don't really talk about them outside of exploit development. There are some tools that are made that are actually the results of debugging work that people have done. For example, Mimikatz, right? As an attacker, we know we run Mimikatz, we get creds, but the work that goes behind developing the functionality of Mimikatz involves that guy sitting in WinDbg and staring at assembly all day and all sorts of function calls, right? And so even though we as consumers of these tools may just know point and click, right? There's a lot of work that goes behind developing these tools in the first place. This also includes like any tool that involves hooking or injecting into processes, right? Anytime that you are using a tool, right, that means that someone had to go figure out how the particular process works, right, the calls that it makes, and anything that involves that usually involves some sort of debugger or things like that. So here's an example of Mr. Gentle Kiwi working on Mimikatz. This is way back in 2015, right? So he was deep in WinDbg even back then as he was developing Mimikatz, and occasionally he'll post like screenshots. I couldn't find a more recent one, but like he'll post screenshots of him in WinDbg and working on new functionality. So let's talk about .NET debugging specifically. It's like a shadow effect. All right, anyway. So there's two main types of memory dumps, right? We have the user level versus the kernel level, where the user level are typically the processes versus the kernel level might involve the entire machine, the types of things that you would probably find in like forensics, right? The whole memory dump of an entire computer. But we're going to focus on dumps of a single process that are using .NET managed assemblies. So really any process that's been written with the .NET framework or .NET Core, just .NET. Right? And there's definitely a lot of ways to analyze .NET memory dumps. So there are some tools, but these tools that are for memory analysis are usually meant for engineers, right? They're meant to help them figure out what went wrong. So like performance analyzers and sort of tracing where some of their code might have been faulty. And it's usually sort of meant for dumps that are a result of a crash, not an intentional dump of a process that you may have taken. So you have things like WinDbg with the SonneStrike DLL. If you were to download WinDbg nowadays, you really don't have to worry about it. If you get the new WinDbg preview, it actually comes with it. But prior to that, you had to go out and grab the DLL in order to do the sort of analysis for .NET processes in WinDbg. There's a story, but I'm not going to get into it. It actually wasn't that interesting. I don't know why I put that in the slide. So this Visual Studio, and Visual Studio has a bunch of performance analyzers to help technicians or engineers figure out what helped cause a crash of their process. There's a whole blog post about it if you're interested on the dev blogs at Microsoft.com. There are some new global tools that are written in .NET Core. and they're meant for .NET Core 3.0 and up. They're command line tools. They're cross-platform, so they work on Windows and Linux operating systems, and the other one, Mac, OS X. And they don't require any sort of native debugger in order to use them. And then finally, there's a library, which you can go check out on GitHub, called CLRMD, which is the Microsoft Diagnostics.Runtime namespace. And this is a library that's used for introspection of .NET processes and dumps. So that's live introspection. So if a .NET process is running, you can sort of use it as a debugger and build your own tools around that. And it supports both the .NET framework and .NET Core. So there's some commands that are similar regardless of whether you're using WinDbg or the .NET tools. One of them is dump heap. And dump heap will display information about objects that have been garbage collected and some statistics about those objects as well. Then we have the dump method table, which displays information about the method table at the address. And the method table is sort of think of it sort of a schema for like a class, right? You create a class in any language, and you have a schema of what the attributes and the properties are and all that stuff like that. So we consider that to be the method table. Then we have dump object, which dumps the actual object, which is an instance of that method table. And then GC root, which we're not going to get into today, but it displays information about references to the object. So if I have some sort of like system.string, right, object, I can see what objects are pointing to this string. It's what I was told. I've never actually run it myself, but I was told that it's really expensive because now you're asking the you're asking the dump, everything that points to me, please tell me what that is. And when you have like large memory dumps, like 16, 20 gigabytes, like it could be a lot of processing. So you might want to use that sparingly. There are some .NET decompilers, which are the tools to really just decompile the .NET assemblies back to source code. There's ILSpy, which is a little older, but it still works. There's a VS Code extension for it. If you happen to have managed libraries in your folder, you can just sort of decompile it right there in VS Code. There's Visual Studio, of course. You can do that. The one I prefer is .peek from JetBrains. It's really easy to use, and it also interfaces with Visual Studio if that's what if that's the environment that you like. So we're going to show you what decompiling a .NET assembly looks like. That is WinDbg. So here I have .peek open, and I know the column on the left is pretty small, but we're not so much interested in that. I'm just going to open up this executable that I have sitting around here, and it's called keyvault.py.exe. We're just going to call it keyvaultmanager.exe. It's just misnamed. And I open it up, and then on the left side, let me see if I can zoom in just a little bit. Yeah, there we go. We can see things like it pulls the metadata from this assembly, pulls the resources that are involved, the references. So what DLL, what managed assemblies does this program reference, right? So Azure Core, Azure Identity. We see a couple interesting things in here, right? So I know that I can just tell from looking at this between Azure Identity and Azure Security Key Vault Secrets that there is some identity that is being used probably to retrieve a secret or set a secret, right? Either way, it's an identity that has access to a key vault, most likely, just common sense. And there's a couple of other things in here too, right? The security cryptography algorithms one is pretty interesting to me, just because that means that something is being encrypted at some point in time. And then as we keep going further down, let me make sure I use the right key on it. All right, we can actually pull out the source code, and we can see that this particular library has this particular program has two major functions, right? It has its main, and then it has a function called decrypt. So here's the main, and I'm going to just zoom in here. That's all we need. There we go. And sure enough, right, this main reaches out to a key vault, and actually first it reads a key from some key on disk. And for the purposes of the demo and the rest of this talk, we're going to pretend like this key is not on disk, right? We're going to pretend like it's coming from somewhere else, just to sort of just trivialize this demo. It reads this key, and then it reaches out to a key vault, and it gets all the secrets in the key vault, and then it decrypts the secret. Here's a comment with the format of what the secret looks like. So there is a message, which we will assume to be the value. There is a nonce, which is used for one-time encryption, so you should only be using your nonces once. And then there's a tag, which tells me that before I even go any further, and even though I guess I kind of already know, the combination of these three suggests that it's an AES encryption, right? Which sort of is backed up by the fact that we saw this system security cryptography algorithms, right? So we can assume that whatever is being encrypted or decrypted is coming out of that particular namespace. And sure enough, if we look up, I guess generally you would start at the beginning of the script and not at the bottom. But if we go up here, we can see that there is a call to AES GCM, and it is taking the secret that we pull from the key vault, decoding it from base 64, and then decrypting it with the GCM algorithm, right? So there's a couple things that we know. So we know that every secret has this format, right, based on the comment and based on just how the decryption function works. We know that there is a key that is read into this program in order to decrypt it, but we don't know what the key is. And we know that all it does is just prints out the results of the secret being decrypted. So let's talk about analyzing a dump of this process. But first, we're going to go off topic again. So a couple weeks ago, only less than a week before Black History Month, BuzzFeed decided to say that Beyonce was holding a hard drive. She was not holding a hard drive. There's an RCA port on the back of this, right? And it just turned out to be like an MP3 player. This has nothing to do with the topic. Again, it's just really off topic. I just thought it was funny because that's clearly not a hard drive. Anyway, so we're talking about attacking a dump. We don't care about things like the threads, counters, and performances, right? I don't care how performant your process is. I want to know what the secrets are in your process. We want those secrets and the credentials if there are any, right? Now, cloud services are really good for this type of information because when you have things like serverless technologies, right, all it is just somebody uploading their code to the cloud, it executes. And in the case of maybe like a web app or something, if it is exploitable and an attacker gains access, you're typically not going to find the normal sort of things. You may find like managed identities, right, an identity that represents that object in the cloud. You may find references to databases, whatever the back-end thing is. It's a little different. You're not going to go as in-depth on your post-exploitation as you would on premises, right? The way that you look for lateral movement in the cloud is different than the way that you would look for it on premises. I guess that's what I'm getting at. But we can still find some goodies on workstations and servers, and these are user workstations and on-premises servers in .NET processes. Sometimes live memory analysis is preferred, but it's not always possible. There are some situations, and we've had two on our team in the last year, where live memory analysis was not possible, but we found some dumps that we were able to analyze. And tools like KeyThief, if you're familiar with that comes from, I believe, SpectreOps. And what it does is that it uses CLRMD, which we talked about is that C# library, to inject into a key pass process and then force the decryption of secrets, whether or not the user is trying to do it. So you can attack a process live, but we're going to talk about just attacking or looking through dumps themselves. There's lots of other tools like that, like KeyPass, that do that. So why are we using strings or grep? Well, tools like strings and grep, they look for strings of defined lengths and endianness. If the strings are defined in the source code, you might see them in the dump. But in C#, strings are like this weird mix of managed code and unmanaged code. So a system.string object is a .NET object, but underneath it's still calling the C objects that are behind it to be, and those are represented as unmanaged code. Managed objects are structured, right? And strings, the command strings, is not really meant to understand structured objects, right? It just looks for plain text strings. So in a large dump, how do you really know what's relevant to the other objects that you're looking for? If you're talking about again, 20 gigabyte dumps, Like, looking through strings isn't really going to tell you much. You might find things in there. You might get lucky. And you might find like big blobs of strings, maybe like access tokens. Those are pretty noticeable. But you generally want to use the tool that is most appropriate for the job. Some of the things that you can't see are secrets that are just straight up bytes. So for example, AES keys are typically, symmetric AES keys are typically just a string of random bytes. You're not going to see that in strings or grep command. So we're going to go over two scenarios. One is this key vault manager, and we're going to look through a dump of this key vault manager. And as we mentioned, all it does is retrieve secrets from a key vault, it decrypts them, and we're going to say that we found a dump of this program somewhere. The other scenario we're going to go through is we found our way to a host where a user is logged in, and we took a dump of their PowerShell session. Why? Because PowerShell is a .NET process, right? It's written on the .NET framework, and so we can analyze it the same way that we analyze any other .NET process. Wow, I just jumped to the end of my slides. Wow. Anyway. So here we have the new WinDbg. If you haven't seen it, it's a lot more user-friendly looking than the previous WinDbg. That's just my opinion. And I'm going to open up this key vault dump here. So I'm going to zoom in as much as possible. All right. So the first thing I want to do is, and I may not have to do it here, but I'm just going to show it anyway, is that when you load this dump, you may actually have to run this command, analyze v. And the reason you have to do that is because WinDbg needs to reach out to the Microsoft symbol server and pull out all the relevant symbols, debugging symbols, that it can find that are in this process and sort of just pull them down from the server and help you analyze, right? If you don't have the debugging symbols, you're going to find yourself doing a lot more work, right? When you compile a binary like .NET, it always has like that .pdb file, right? Those are the types of files you want for your debuggers. And so we just went through, analyzed the whole thing, and now I can run some commands. So the first thing I want to know is, when this dump was taken, what was on the heap? And we can run this command. It's all the way at the bottom. But can I spit this? No, I can't. 1 second. All right, never mind. All right, so we're going to say dump heap, and I want to know, give me the statistics. I don't want to know everything, just give me the statistics, and that gives you the type of objects that are sitting on the heap, as well as a count of all of them. So here there's, lost my cursor, there we go. Here there's 2,115 system.strings. I can see that there's 391 Azure Security Key Vault secret property objects in here, right? And this tells me that, okay, at the time this dump was taken, there was at least this many objects in there. And so we can go inspect those objects and see what they contain. You can also do a filter, because now I know that there's Azure-related stuff in here. So I'm just going to type, I'm looking for this type, and this type takes a string, which gives you all objects that have this substring in them. So if I do Azure, it's just going to give me every object type that has Azure in it, right? And this works, of course, for any. I work at Microsoft, so like I'm using Azure, but this is the AWS, GCP, whatever. It doesn't really matter. You can search for any type. You can look for things that are in the framework itself, right? So I can look for system, and it'll pull back everything that has system in it. And so as I'm looking through, I'm curious about a lot of things. In this scenario, we're pretending like we didn't see the source code, right? We only found the dump. So we don't really know what the program is doing, even though we know what the program is doing. And I'm going to look through, and I'm going to try to find interesting things. Like, for example, here is an Azure Identity, Azure CLI credential. That's interesting to me, because this means that this object in memory was holding the credential that was used to authenticate to the key vault. And so on this left side here is the method table. We talked about, right, the method table is the schema for the object, and it's saying that the method table for this CLI credential is right here. Before we go on, we're going to keep looking for other things, and we're going to see things like I can't find it, so let me do the proper search. Secret. here we go, the 191 key vault secrets, right? So these are all representations of the actual secrets as they're seen by .NET. So there's two things that we're already interested in. That's the credential and that's the secret. So we're going to start with the secret because it's smaller and easier to go over. So if I click on here, because the new WinDbg just sort of lets you click your way through a lot of things, you can pull this method table for this key vault secret. And what it gives you is every instance of a key vault secret and the address that it lives at. So all of these right here on the left-hand side are addresses, and the right are all the method tables, which is why they're all the same. And really, we can pick any one of these, and it's going to take us to the instance of that object. Also, when you're clicking on things, there are commands that are running behind the scenes, right? So like, if I click on this, it's actually running dump object and giving it the address of whatever it is that I click on. So we're just gonna pick a random one, and this, one of the random secrets, right? It has a properties value, it has a properties field, and it has a values field. Well, right after that, I know that if I'm writing in .NET and I want to pull the value of a secret that I've pulled, like from a key vault, well then I call like secret.value, right? So I'm interested in what this value is. And right off the bat, if you click this, we get the actual secret that was contained, that was pulled from this dump, right? That was pulled from the key vault, right, at the time. I don't know what secret this is. I know I have the value now, right? And it is the message, which is that base 64 encoding, the nonce, and the tag, which is basically what we saw in the comment in the source code earlier. I can go through the properties, and I can just sort of click through things until I find something else that's really interesting. So for example, the identifier of this secret contains the ID, which is the resource, the object ID, which is the entire resource ID that Azure sees. And that also consists of the vault URI, the name, and the version. So the ID actually has all three of these, right? So we're just gonna look at the ID itself. And you can see that it is a URI scheme. And keep in mind, like, as you're clicking through these, on the right here in the type, you can also see the type of object that they are. So I know that a string representation of a URI object is going to give me the full string, like as humans would read it, right? So if I click on this, well, now it tells me that here's the string, and that was at Turdshovel vault.azure.net. This is some secret 25, right? So now we have the name of the secret, we have the value of the secret. If we wanted to, we can go back to the credential object. And we can try looking through here. The problem is, some of these .NET objects are very large, right? There's a lot of pointers. There's a lot of pointers pointing to other things left and right. And so we can try to go through this. And you notice that there's a lot more values here. If I click on any one of these, it's going to have a lot more things in them, right? And it gets kind of messy trying to go through all this stuff one by one, because especially when you have a large dump, right? I think there are 100 secrets. There's 100 secrets in this dump, and if I would try to go through these one by one, right, I'd be sitting here clicking all day. Really got time for that. Before we move on, there's another thing we want to look at, and that was, we remember that the value of those secrets are encrypted, right, with GCM. So we can look for an object, not that. We can dump the heap, looking for the object that has GCM in it. And sure enough, there's 190 of them. So if we click on this method table, and we go through the same process again, we're going to look for, we're trying to find the key, right? Wherever that key is in memory somewhere, and it's a set of bytes. We don't know what it is. And I'll be honest with y'all, I actually don't know what the key is either, because I forgot to git push my samples before I left home, and so I had to rewrite this morning. So I have no idea what the key is, and we're going to learn what this is together, right? I know where the key is at in memory, but I don't know what it is. And so as we look at this GCM object, right, there's a key handle, and there's two fields that are sort of static fields, and they tell you what the minimum and maximum size of the nonce can be, which is, in this case, 12. The recommended is 16. I guess C#, there was a whole issue about it on GitHub, and it's kind of wild. But the recommended byte size is 16, not 12. And there's a tag size, and there's this key handle. But if we click on the key handle, it gives us an address to another handle. And it just sort of stops there, right? We can go look at this in memory and not really understand what's happening when we get there. So first, before we look at that handle, we're going to just go look at the object in memory itself. What does that look like, right? And you'll have to forgive me because there's no way for me to effectively zoom in on this memory thing, so I'm going to try to do the best I can zooming in, but they did not make this the easiest to do. All right, so we're going to go to that address. I just copied and pasted it. And there's a couple of things that, as I'm looking at this, now that I know, right, I can say, okay, well, there's the key is right here on the screen. How do we get there? How do we get to that point? Well, the first thing, we're sitting at this pointer that is on the top. Do y'all need me to zoom in a little bit more? Yeah? Are you good? You zoom in a little more? Just a little bit. I don't want to, overdo it. Hopefully that works a little better, right? Right. Lost a spot, F8. Okay, we're back here. All right, so the first thing that we see is what appears to be a pointer. The address is 7F, F8, 54, F5, 9A, C0. This address is the method table, right? This says that this object in memory starting right here is an AES GCM object. That method table address that we looked at before that we sort of just clicked through. So this tells me right here that that's what that is. The next thing is that key handle pointer that didn't lead to anywhere else. So this is the next address that is sitting in memory right at the beginning of the method table. So the question is, where is the key in all this, right? Where's the actual key? How do we find that out? Well, if we go look at the source code, oh, wow. If we go look at the source code, we're going to see a couple of things. This is what the GCM object looks like, right? We have the nonce byte sizes. We saw that in WinDbg, right? We have the tag byte sizes. We also saw that. And we know that when we instantiate the object, it runs this import key function. So what happens to that key? Where does it go? Well, we're going to look at the Windows implementation of this AES GCM object because the Linux implementation uses OpenSSL, whereas Windows does not. And we're going to see that here's the key handle object that we just saw, right? This key handle is a representation of this interop, and so this is a low-level call, an interop, for bcrypt at bcrypt import key, and we sort of just pass it the key. So we're going to follow this key handle because that's where we want to go. We know it has the key in it somewhere. As we keep moving on, we see a couple things that are really interesting. One, we notice that that key handle returns what's called a safe key handle object, right? And as we sort of continue down this code, we can see things like there's a key size that gets pulled, which is the length of the key. There is a blob size, which is the length of the key data blob header, which we'll talk about in a second, plus the length of the key size. So this key size and this blob size are sort of represented somewhere in memory. But it's represented sort of as it's represented here in this actual blob object as we start making our pointers and doing all the crazy things. So we take the header, this blob header, which we'll get to in a second, and then that header points to some magic number or magic header. Then it also points to a version, and it points to the size of the key, which is, in our case, 16 bytes. So what is this? And then later, the key gets copied to this blob, right? So what is the key header, or the blob header, right? If we look down here, here's the actual struct for that blob header. And we see that the magic header is this 4D, 42, 44, 4B. Right? This is the magic header that says, this is where your AES GCM key is going to start. The version number is 1, it's some arbitrary number. We don't really care so much about that. But this means that as we look at the struct, that there is going to be some value of 4D, 42, 44, 4B, followed by a 1. And they're both going to be 4 bytes each because they're unsigned integers. And so this 1 is going to be represented by 0, 1, as we look at it, 0, 1, 0, 0, 0, 0, 0, 0. And then after that, here comes the key. So if we go back to WinDbg, if I can get the magnifier, we're looking for that value, right? Does anyone see it already? I know maybe it's a little too small, but anything that looks like a header up here? Notice we're not looking further below around that secret value 30. But if you can't see it, give it a little bit of time. But as we go, through this struct, here it is, right? Here's this header, and it's represented by the letters KDBM. This KDBM is also listed somewhere else in the source code, and it's like just as a comment saying this is what you're going to see in memory. So it's really convenient to notice that. But this is the actual header. It tells us that this is where the key starts, followed by that 1 that we mentioned, right? So the version. So 0, 1, 0, 0, 0, 0, and then followed by the key size, which is 32 bytes. I said 16 before. I'm sorry. I meant 32. It's actually 32 bytes. So this represents, this block of 4 bytes represents the key size. And then right after that, here comes the key. So this is our key right here. Like I said, I didn't know what the key was when we started here, but now we just found it. We went through, we looked at the not only the struct in WinDbg, but we referenced the source code to understand how the struct was built, what indicators we should look for the key, and we can go back into WinDbg and now finally pull this entire GCM key out of here. I would pull it out and decrypt it for you, but guess who forgot to git push their decryption script this morning or yesterday? So, but basically, this is the GCM key. We can pull this out and do our decryption of the key vault secret, right? Because now we have the nonce, we have the tag, we have the value, which is the ciphertext, and we have the key, and we just throw those values in the magic machine, and we can decrypt the key vault secrets. Yay! All right, we're gonna do one more, and this one is PowerShell. So I took a dump of a PowerShell process, and it's very similar in its nature, right? It's .NET. What's happening? Gotta stop debugging first. Yeah, see, I was trying to reach the menu, but my window kept moving. Wild. All right. So we're gonna open up this other dump file. Fresh, bam. And we can do sort of the same thing, but the problem is a process like PowerShell, which is so complex, right? There's a lot of stuff going on underneath there. If you take a dump of a PowerShell process, you're likely to get between 200 and 600 megabytes of memory, even if you haven't really done anything, right? That's just how massive it is as a framework. And we can look through here doing the same dump heap tricks, right? Or command, I should say, not really a trick. And we get similar objects, right? Similar object structure. We get the counts, and there are some things that are interesting in a PowerShell script or in a PowerShell session. For example, if I were to open up PowerShell and I pressed up, right, I would go to my history, right? Which means that there is an object in a PowerShell session that represents not only the active history of that session, but also the history that you would find on disk in the PowerShell history file itself. There's other things like, for example, when a script is run, so you're running a PowerShell script and it gets compiled into script block data, right? So a lot of people do their script block logging. Hopefully, if you work in a SOC and you're logging all your things correctly. But that is represented by a .NET object, which we would be able to find in here if I had run a script, and I had not, now that I think about it. But we can find things like my history info. So if I do a stat type for history, I come across 48 history info objects, which represents 48 commands that I've run in the past in my PowerShell session. More interestingly, there is a history info array, which is actually just a list of all the history info objects. So I don't actually have to go one by one through the history info. I can just pull the array and pull every single command that I've run in my session. So if I click on this random one, for example, this is an array. So we're just going to sort of click through. This is the element 0. I click on command line. And you can see that I ran cred, get credential, right? So I created some credential object in this PowerShell session. Now, underneath, when you do something like get credential on Windows, only on Windows, that credential object, right, that secure string value for your password, gets encrypted by dpoppy. I call it DPAPI. I call it dpoppy because that's also my stripper name, and so it all makes sense to me. But that particular object in memory is only encrypted in a way that the process itself can decrypt it. So you can't actually take the value of those bytes and try to decrypt it outside of the process because it's specifically, that memory is specifically encrypted with the same process flag, right? So if you were to try to pull this credential out, it wouldn't really help you in that spot. And that's where things like live debugging and injection, you could actually force all the secure strings to be decrypted in memory in another user's PowerShell session without really asking them to do that, right? But on Linux, DPAPI, dpoppy doesn't exist, right? And it turns out that like everything on Linux is just like plain text in memory. It's called secure strings still in Linux because it doesn't get logged, right? You're not gonna see it in your logs. It's never going to be accidentally printed out. So it's a secure string, but by the implementation, if you were to dump a .NET process, a PowerShell process in memory on Linux, and you were to look for a secure string objects, you would see them in plain text. Here we're not gonna be able to see that, but that's just something that's really interesting. And so I can pull this get credential down and do all my crazy things, but that's a lot of work, and PowerShell is very large, right? So as a result of not wanting to click through WinDbg all the time, I wrote a tool. And this tool is called Turd Shovel. Right, that's my logo. It's on GitHub, github.com/daddycocomain/turdshovel. And I'm just gonna give a demonstration of that. Ignore that, that was a CTF flag that you probably saw the QR code for. So I've already installed it. It sits on PyPy. And you know what? Let me actually do the actual slide for it first. All right, so Turdshovel is a CLI tool that allows you to dump the objects from .NET memory dumps without actually having to click through everything, as we just did. Again, there were 100 secrets in that first dump. I'm not gonna sit there and be clicking all day. I don't have time for that. It's only usable in Python 3.8 specifically for now, and that is because of a dependency on Python .NET, which has not yet been updated to its new version. And so you can only use it with Python 3.8. Eventually, when Python .NET supports more versions, officially it supports more versions, we can go up to 3.10, I think. And it also uses CLRMD, which is a C# library underneath. It might make sense to write Turdshovel in C#, but I don't do that. I don't write in C# unless I have to, so nah, we good. So let's let's open this up. Go to my samples folder. And I have this little ASCII poop, it's cool. And the first thing I'm gonna do, right, there's a help menu. That's not how you spell help. There's a help menu. But the first thing I'm gonna do is I have to load the memory dump, right? So I'm gonna load. this dump. And what it does, it goes through using CLRMD. It finds all the unique object types in .NET, the things that we saw in dump heap early in WinDbg, and lets you just start playing around with this. We can run the same commands, right? Dump heap, and I can do a filter for, again, Azure, right? And I get sort of a similar view to what we saw at, oh, whoa. I forgot, you can't resize this because of reasons, so anyway. And so we're getting a similar view to what we saw in WinDbg, right? We have the objects themselves, the sides of the objects, and the address that they're at. Then we can do things like, well, dump an object, right? And so if I look for something like a key vault secret, there's going to be one in here somewhere. Well, let's just do this then. Dump heap. That's not right either. Filter secret. If I pull this object, right, sitting at this address, this is the key vault secret. If I dump object, well, now I get a JSON representation of what this object is without having to go through all the nonsense of clicking each field individually one by one, because that's way too much work. So the first thing that we see, right, was that value, and we can see the JSON value that's here. We can see other information about what a key vault secret object holds, right? So when was it created? When was it updated? Does it expire? Is it valid before or after a date? These are all settings you can set in Azure for a key vault secret. The name of the secret itself was some secret 30. The URI for the vault was Turd Shovel vault. And we can just dump an entire object in .memory. Now, you can't do this for all objects because some objects, like the ones in PowerShell, are like super large. And even though, I mean, you technically can dump it, I wouldn't recommend it. So you sort of have to know like what you're looking for and be very selective in dumping, particularly objects, because a lot of them may have pointers that point to themselves or reference themselves or reference something that referenced it, and it's like this whole circular loop. So I tried to stop that as much as possible, but bugs are bugs, right? But again, that's just one secret, right? So what if I want to dump all the secrets? I don't really care what they are, I just want to dump all of them. Well, then I can do dump type, and I can do types, and I get this autocomplete for all the types that are found inside of this process, right? Those unique types that we saw when I loaded up the program. And then I can do something like Azure dot, was it security? And you can go up and down the menu, right? And what this will do, when I run this will dump every single secret that is found in that process. And you can save it to disk if you wanted to, right? Hitting save and then save true, and it will just save everything to disk. So now you have JSON representations of every .NET object, all these secrets, that you can decrypt with the key that you found for GCM. You can also do something like memory, and if we go look at the, let's see, so dump types, it was system, security, ACM, GCM. Oh, you know what, actually, dump heap. I need that original address of the AES GCM object. I can actually go to this point because remember that this object first had the method table, then it had some other values, and it had the key. I can just dump the memory with dump mem and add with the address of any one of these objects. And I'll say the length was, I think it was about, we'll just say 64, I don't recall off the top of my head. And sure enough, yep, there's that KDBM that we saw, and we can pull the bytes out of the memory directly without having to go through all that stuff again. So once you start to learn what the structure of your objects are that you're looking for, you can go directly to those objects without having to do all the clicky things. So there's that. That's my cool contribution to society in the last couple of months. And that is it. So Do I have any questions? Are we doing Q&A here? Is that the thing? Okay, yeah, any questions? Anybody?
You got a question?
Oh, no, I was just admiring the knee, that's all.
Oh, yeah, thank you. Well, cool. Sounds like there's no questions.
Any questions online?
Not been anything in the Q&A yet.
Okay.
Was that a no?
I asked her if there were any questions online.
Okay,
Nothing? Nothing
cool.
yet?
Then we good. We Gucci. All right. Well, I'm Leron. You can catch me at MCOMI on Twitter. Give me a follow. And thanks for coming out. Appreciate it.